All right, so get this. Imagine test driving a quantum computer right from your desk. That's what we're diving into today, quantum emulators.
It really is like a sneak peek into the future of computing, isn't it? Getting to experiment with quantum algorithms and applications before the real quantum computers are everywhere. It's like glimpsing a whole new world.
Okay, so let's unpack this. What exactly are quantum emulators?
So essentially, they simulate quantum systems on our normal computers using clever algorithms and tons of computing power. Think of it like playing a video game, and the graphics are so real, it's practically like real life.
So like a video game, but for quantum computers.
Yeah, exactly. And it's super important because actually building and maintaining a real quantum computer is incredibly expensive and complex. So emulators make it way more accessible for researchers and developers to test things out and experiment with quantum algorithms without, breaking the bank.
Makes sense. So how powerful are these emulators then? Can they simulate any quantum system?
Oh, there has been so much progress. Some emulators can now simulate systems with up to 40 qubits, and those are the basic building blocks of quantum information. To put that into perspective, that's like juggling 40 coins and keeping track of every single combination of heads and tails at the same time.
Whoa, 40 qubits. That sounds pretty intense.
It is. It's a huge jump from just a few years ago. And we're not even just talking about raw power here. There are all these different types of emulators, each with their own strengths and quirks. Like, for instance, Intel's quantum simulator, or IQS, is great for simulating some types of quantum algorithms. And then you have Quest, which is designed to be super flexible and can run on different types of computers.
So it's like having a toolbox full of different emulators for specific jobs.
Yeah, that's a great analogy. And to make things even more realistic, some advanced emulators can actually simulate the noise and errors that happen in real quantum systems. One example is Callisto. It was developed by C12, and it uses realistic noise models. So it's like mimicking the behavior of real quantum devices. That way, researchers can see a much more accurate picture of how their algorithms are going to perform in the real world.
That's really cool. It's like a flight simulator that not only like mimics the physics of flying, but also throws in some turbulence and wind shear.
Exactly. It's all about getting as close as we can to the real thing so that when we finally do have all these powerful quantum computers at our disposal, we're ready to go.
I see why these emulators are such a big deal.
Yeah.
So how are these being used today? What kind of cool stuff are people doing with them?
Oh, there's a ton of activity. One of the most important things is developing and testing quantum algorithms. Those are the algorithms that can leverage all those unique properties of quantum mechanics, like superposition and entanglement, to solve problems that are impossible for even our most powerful classical computers to handle.
Superposition and entanglement. Those sound straight out of Star Trek.
I know they do sound very sci-fi, but they're actually real and they form the foundation of quantum computing. Superposition means that a quantum bit or qubit can exist in multiple states at the same time. It's like a coin that's both heads and tails at the same time until you actually look at it. Then entanglement, that's like this spooky connection between two or more qubits where they become linked and their fates are intertwined.
Okay, I think I'm following you. So how do emulators help us design algorithms that use these properties?
Okay, imagine trying to find your way through a massive maze. A classical computer would have to go down each path one by one until it finds the exit, right? But a quantum algorithm, because of superposition, could explore all the paths at the same time and find the exit way faster. Emulators let us test these algorithms and tweak them before we have a quantum computer powerful enough to run them on.
It's like a cheat code for complex problems.
Exactly. And it's not just about speed either. Quantum algorithms could potentially solve problems that are completely unsolvable for classical computers no matter how much time we give them. That opens up some really exciting possibilities in materials, science, drug discovery, even artificial intelligence.
This is really cool stuff.
Yeah.
Are they only useful for algorithm development?
Oh, no, not at all. Emulators are amazing for education and training, too. They provide a way more accessible way for students and professionals to learn about quantum computing and experiment with quantum programming without needing access to expensive and complex hardware.
So it's like Quantum Computing 101, the emulator version.
Exactly. And because emulators can run on pretty much any computer, anyone with a laptop and an internet connection can start exploring the world of quantum computing. It's opening up the field to a much wider audience, which is so important for driving innovation and progress.
That's awesome. So we've got algorithm development and education. What else are they using these emulators for?
Well, they're also crucial for software development. As we move closer to having practical quantum computers, we need to build the software that supports these powerful machines. Emulators are helping developers create and test quantum software and tools, so it's like paving the way for a whole quantum software ecosystem. It's kind of like building the roads and bridges before the cars can drive on them.
That's a great way to think about it. So emulators are doing a lot of the groundwork for us to get to this quantum future. But, building these actual quantum computers is expensive and complex. Are there any downsides to using emulators? I mean, can they really replace the real deal?
That's a really good question. And the answer is unfortunately no. Emulators are super useful tools, but they do have limitations. The biggest one is scalability. As you increase the number of qubits in a system, the computing resources needed to simulate it grow exponentially.
So the bigger the quantum system you're trying to simulate, the harder it gets.
Exactly. It's like trying to fit the ocean into a teacup. At some point, our computers just don't have the memory or processing power to accurately simulate a really large quantum system.
So we hit a wall in terms of how big we can go.
We are always pushing the limits, but there will always be a point where classical computers just can't keep up.
It's like a constant race against this exponential growth.
Well,
But what about other limitations?
you've also got the performance gap. Emulators are getting better all the time, but they can't match the potential speed and efficiency of a true quantum computer for those really tough, large-scale problems. It's kind of like comparing a horse-drawn carriage to a supersonic jet. Both can get you from point A to point B, but the jet is going to be way faster.
Okay, so there are limitations.
Hmm.
And what about replicating those real-world complexities of quantum systems? Those are really sensitive to noise and errors, right? Can emulators accurately capture that?
That's another big challenge. Quantum systems are super delicate, and they're prone to errors because of things like decoherence, which basically means that the quantum state loses its quantumness over time due to interactions with the environment. It's like trying to build a sandcastle on a windy beach. The environment is constantly working against you.
So you're trying to simulate a hurricane, but you have to factor in every little detail.
Pretty much. It's super complex, but researchers are developing more advanced noise models and error correction techniques to make the simulations more accurate.
Well, that's good to hear. So even with these limitations, quantum emulators are a really important step towards unlocking the full potential of quantum computing.
Mm.
What do you see for these emulators in the future? What advancements are coming?
The future is looking bright. We're going to see big improvements in the accuracy of emulations with more sophisticated noise models, better error correction techniques, and even hybrid approaches that combine classical and quantum resources.
Hybrid approaches, what does that mean?
Imagine merging the best of both worlds, the power of classical computers with the unique abilities of quantum systems. There are companies like Commutator Studios already working on these hybrid models, trying to figure out how to combine these two computing styles to create something truly amazing.
It's like combining two different superpowers to make an ultimate supercomputer.
Yeah, I like that. It's about using the strengths of both approaches to push the boundaries of what's possible. And we're also going to see more specialized quantum developer tools coming out, which will make it easier for developers to create, test, and deploy their quantum applications.
That's great news for all the aspiring quantum programmers out there. It sounds like the future of quantum emulators is all about pushing those boundaries, bigger simulations, greater accuracy, and even more powerful tools.
And remember, we're still just in the early stages of quantum computing. What we're seeing with emulators is really just the tip of the iceberg. The potential applications in fields like medicine materials, science, and artificial intelligence are mind-boggling.
It feels like we're standing at the edge of a whole new world, and the emulators are like our maps and compasses.
Exactly. They're helping us get ready for a future where quantum computing isn't just a possibility, but a reality that changes everything.
So we've established that I'm on board with this quantum adventure. But let's talk about accessibility. We know that real quantum computers are super expensive and not readily available. So how can someone explore this quantum realm without, needing $1 million?
That's where the cloud comes in. Cloud-based quantum emulation is making quantum exploration way more accessible and affordable than ever before.
Oh, so it's like those cloud gaming services where you don't need a crazy expensive gaming PC to play the latest game.
Exactly. Instead of having to build and maintain your own expensive quantum infrastructure, you can tap into the power of cloud platforms that offer these quantum emulators as a service.
So anyone with an internet connection can potentially start experimenting with quantum computing.
Pretty much. And there are already some great examples out there. Scaleway's Quantum as a Service, or QIAS, is a fantastic example. They give you access to a range of quantum emulators powered by different hardware, from CPUs to GPU clusters. It's a game changer for researchers, developers, and students who want to get into the quantum world.
I love the idea of making this technology more accessible. So what are the specific benefits of using these cloud-based emulators? What makes them so great?
Well, first off, cost effectiveness. You're not spending millions of dollars on a quantum computer. You can just subscribe to a cloud service and pay for what you use.
That's definitely more appealing to my wallet.
Yeah.
What else?
Speed. Cloud-based emulators let you experiment and develop things way faster. You're not waiting around for access to a physical quantum computer. It's like having your own quantum sandbox to play in.
I'm all about faster results.
Yeah.
But we talked about the limitations of emulators in terms of how much they can simulate. Does using a cloud platform change that?
It does. Cloud platforms have all those vast computing resources, so you can often simulate larger quantum systems than you could on your own computer. It's like upgrading from your regular laptop to a whole research lab.
So cloud-based quantum emulation is really breaking down those barriers and making it easier for everyone to explore. But let's be honest, quantum computing is still a pretty specialized field, not something you just learn over a weekend.
Hmm.
For people who are curious, but maybe a little intimidated by the complexity, what advice would you give them? Where should someone start learning about quantum programming?
Well, the good news is there are some really user-friendly tools out there to help you get started. We've been talking about emulators, which are great for experimenting, but there are also these things called software development kits, or SDKs, that are specifically made for quantum programming.
SDKs. Okay, that sounds kind of familiar. Are those like the toolkits that regular programmers use to build apps and software and stuff?
Yeah, exactly. Quantum SDKs are like the bridges between the code we understand and the crazy world of quantum computers. They give you pre-built libraries, functions, all these features to make designing, building, and running quantum algorithms easier.
So they're like training wheels for quantum programming.
That's a great way to think about it. And there are quite a few popular SDKs out there, like Cirq, my QLM, CDAQ, Qiskit, Percival, just to name a few. They each have their own strengths and quirks, but they all want to make quantum programming more approachable and less scary.
That's good to hear. So instead of needing a PhD in quantum physics, you can start experimenting with these SDKs and get a feel for how these quantum programs actually work.
Exactly. And they're not just for beginners either. Professional researchers and developers are using them for all sorts of cutting-edge quantum applications.
This is really cool. But I have to be honest, my brain is still trying to wrap itself around the whole idea of quantum programming. It's so different from the regular programming that I'm used to. Can you give me a real example of how someone would go about creating a simple quantum program using one of these SDKs?
Sure. Let's say we want to create a GHZ state using the Qiskit SDK. Now, don't let the name intimidate you. It's a special quantum state where three or more qubits are all kind of in this synchronized limbo together.
Okay, 3 qubits all doing a quantum dance or something.
Yeah, pretty much. And with Qiskit, you can actually create this state using just a few lines of code. You start by defining a quantum circuit, then you apply these specific quantum gates to the qubits, and then you measure the outcome.
And what would this GHZ state actually be used for in the real world?
It's a fundamental building block for all sorts of quantum applications, from quantum error correction, which is super important for making quantum computers more reliable, to things like quantum teleportation.
Wait, did you just say quantum teleportation? We're talking about teleporting objects like in Star Trek?
Not quite. Quantum teleportation is about transferring quantum information, not physical matter. It's a really complex topic, but the GHZ state is actually a key part of making it possible.
Okay, so no beaming people up just yet. But the fact that we can even talk about these concepts and experiment with them through software is incredible. It really shows how powerful these SDKs are for connecting this abstract quantum theory to real applications.
Yeah, exactly. And what's amazing is that even simple quantum programs like creating this GHZ state involve manipulating and entangling qubits, which are things that just don't exist in classical computing. It's like a whole new way of thinking about computation.
It's definitely mind-bending,
Yeah.
but that's what makes these duck dives so great,
Yeah.
right? It's all about exploring the frontiers of knowledge and understanding our universe better. And speaking of frontiers, we've been talking about this exciting future of quantum computing, but we're not quite there yet, are we? What stage of development are we in right now, and what are some of the milestones we're still working towards?
Yeah, you're right. We're not living in a quantum utopia just yet. We're currently in what's called the noisy intermediate scale quantum era, or NISQ for short.
NISQ, that sounds kind of ominous.
It's not as bad as it sounds. It just means that the quantum computers we have today are still pretty small in terms of how many qubits they have, and even more importantly, they're prone to errors.
So the noisy part refers to all those errors we talked about before.
Exactly. These errors happen because quantum systems are so delicate and they're easily affected by noise from the environment. It's one of the biggest challenges we're facing when it comes to building large-scale, fault-tolerant quantum computers.
It's that sandcastle on a windy beach analogy again.
Exactly. But even though there are challenges, the Q era is a time of amazing progress and discovery. We're learning so much about how to control and manipulate these quantum systems, and we're developing new techniques to deal with those errors.
So what's the ultimate goal here? What are we working towards?
The holy grail of quantum computing is what we call fault-tolerant quantum computing, or FTQC. This is where we'll have quantum computers with enough qubits and low enough error rates to really tackle those big transformative problems that are way beyond what classical computers can handle.
And what kinds of problems are we talking about?
Things like designing brand new materials with crazy properties, developing life-saving drugs with incredible precision, or cracking the encryption that protects all of our sensitive data.
So we're talking about breakthroughs that could revolutionize entire industries. But we're still a ways off from achieving this fault-tolerant quantum dream, right?
Yes, but we're making good progress. Error correction techniques are going to be key to getting there. Researchers are exploring all sorts of different approaches, including some really interesting ones like measure-based computation and fusion-based computation.
Measure-based and fusion-based computation. Those sound super complicated.
They are. But the basic idea is to find clever ways to encode quantum information so that it's less affected by errors. It's like building a shield around your delicate quantum data to protect it from all that noise.
So it's like a race against errors. We're trying to build these quantum shields faster than the noise can break them down.
Exactly. And the stakes are high because these error-corrected, fault-tolerant quantum computers have the potential to change the world in ways we can't even imagine yet.
Okay. I'm both excited and a little scared at the same time. Excited about the possibilities, but also kind of worried about the downsides. You know, we've all seen those sci-fi movies where the super intelligent computers take over the world.
I get it. It's important to think about the ethical implications of any powerful technology. But quantum computers are tools at the end of the day. They can be used for good or bad, just like any other technology.
That's true.
Yeah.
It's up to us to make sure these powerful tools are used responsibly. But speaking of potential downsides, there's one specific concern that I keep hearing about, and it has to do with encryption. Is it true that quantum computers could potentially break the encryption that protects all of our online data, our financial transactions, everything?
That's a valid concern, and it's something that security experts are definitely taking seriously.
So it's not just a plot point from a spy movie.
No, not at all. The encryption algorithms that we use today, like RSA encryption, are based on math problems that are hard for classical computers to solve. But quantum computers, with their unique abilities, could potentially crack those codes much faster.
How much faster are we talking?
It's hard to say for sure because it depends on the specific algorithm and how big the quantum computer is. But to give you an idea, some researchers think that breaking RSA 2048 encryption, which is used everywhere, would require millions of physical qubits that are really good at their jobs with very low error rates.
Millions of qubits. That sounds like it's a long way off.
It is. We're still years away from fault-tolerant quantum computing where that would even be possible. But that doesn't mean we should just ignore it.
So it's not an immediate threat, but it's something we need to be thinking about now.
Absolutely. The world of cybersecurity is always changing, and we need to be proactive about developing quantum-resistant encryption algorithms if we want to stay ahead of the game.
So it's like a quantum arms race.
In a way, yeah. But it's also a really interesting challenge that's driving innovation in both cryptography and quantum computing.
Well, that's good to hear. It sounds like there are risks, but there are also some really smart people working hard to find solutions. It's a race against time, but it's a race I think we can win.
I'm optimistic too. The future of quantum computing is full of challenges and opportunities, and this journey is really just getting started. It really is an amazing journey, and that's what makes it so interesting. It's like this fusion of physics, computer science engineering, even a little bit of philosophy as we try to wrap our heads around these mind-bending quantum concepts.
You're totally speaking my language. But let's zoom out for a second, talk about the bigger picture. We've gone through all the technical stuff, emulators, SDKs, the challenges of error correction. But what does all this mean for, like, the average person? How is quantum computing going to actually affect our lives when it finally gets to that fault-tolerant stage?
That's the big question, isn't it? And while it's impossible to predict the future, we can already see hints of its potential to completely transform different industries. Like, let's take medicine. Imagine being able to design drugs with incredible precision tailored to each person's genetic makeup, or simulating these super complex biological processes to understand diseases at the molecular level.
So personalized medicine that actually works, that would be amazing.
Totally. And it's not just about treating existing diseases. Quantum computing could revolutionize drug discovery altogether. so we could develop new therapies for conditions that are currently incurable.
Wow, I'm already feeling healthier just thinking about it. So where else will we see this quantum magic at work?
Material science is another area that's ripe for disruption. Imagine being able to design materials with properties that we never thought possible, lighter but stronger, more efficient at conducting electricity or heat, maybe even materials that can heal themselves.
So a complete materials revolution.
Yeah.
No more clunky tech.
Exactly. Think about what that means for everything from airplanes and renewable energy to the phones in our pockets. The possibilities are endless.
I think my mind just exploded. And we haven't even talked about AI. I know quantum computing is going to be a big deal for AI, but I'm still not quite clear on how. Can you explain this quantum AI connection a bit more?
Sure. Think of it this way. The AI we have today is mostly based on machine learning algorithms that are trained on tons and tons of data. These algorithms are good at spotting patterns and making predictions, but training them can be computationally expensive and take a long time.
So where does quantum computing fit into all of that?
Well, quantum algorithms have the potential to speed up these machine learning tasks significantly. They can analyze and process data way faster, which means more efficient training and maybe even smarter AI systems in the end.
So AI that's not just faster, but also more intelligent.
Potentially, yes. It could lead to AI systems that can tackle more complex problems, understand human language better, or even be creative like humans are.
Okay, now we're going back to the sci-fi realm.
Yeah.
But that's what's so cool about quantum computing, right? It's
Oh.
blurring the lines between what we thought was possible and what could actually happen. But let's be real for a second. We've talked about all these potential applications, but how long until we actually see them? Are we talking years, decades, or centuries?
That's the question everyone wants to know. Even the top quantum experts can't say for sure. The field is moving fast, but there are still some big technical challenges to overcome, especially when it comes to scaling up these systems and making them more reliable.
So patience is key.
Patience and a good amount of optimism. The journey to fault-tolerant quantum computing is a marathon, not a sprint. But the progress we've made in recent years is amazing, and we're just getting started.
That's good to hear. It's like we're watching this whole new technological era being born, and who knows what's waiting for us on the other side.
That's the beauty of it. We're exploring uncharted territory, pushing the limits of human knowledge. It's a time of incredible potential, and I'm really excited to see what the future holds.
I am too. Let's switch gears a bit and talk about where quantum computing is right now. We've mentioned that we're in the NISQ era, which means quantum computers are still kind of small and noisy. But what does that mean practically? What can today's quantum computers actually do?
Well, things are changing all the time. It's a really dynamic field. We've seen quantum computers solve some specific types of problems faster than classical computers, but only for very particular tasks. The real excitement, though, is about their potential to tackle problems that classical computers just can't handle no matter how much power they have.
So it's not just about speed, but about solving completely new kinds of problems.
Exactly. Quantum computers work in a totally different way than classical computers. They use the weirdness of quantum mechanics to explore a bunch of possibilities at the same time. So they have the potential to find solutions that are completely beyond our current way of computing.
That's what makes this so mind-blowing. It's not just a small improvement. It's a fundamental change in how we think about computing.
And that change is what makes it so exciting to be part of this field right now. We're literally seeing a new era of computing being born, and the possibilities are endless.
I can feel that excitement.
Yeah.
So if someone is curious and wants to learn more about this, where should they even start? What resources would you recommend?
There are a bunch of great resources online and offline to get you started. If you're looking for a gentle introduction to the basics, I highly recommend the book Quantum Computing for the Very Curious by Michael Nielsen and Andy Matuszak.
Okay, that sounds like a good place to start. What about something more technical?
For people who want to get into the nitty-gritty details, there's Understanding Quantum Computing by Olivier Ezrati.
Perfect. I'll add that to my list.
Yeah,
And what about online resources? Any websites or platforms that you like?
of course. The website Quantiki is a great place to start. It has articles, tutorials, and links to all sorts of resources. And then there are the websites for the big quantum computing companies like IBM, Google, Microsoft. They have a lot of information about their research and platforms.
So there's no shortage of info for people who want to learn.
Definitely not. And the quantum community is very welcoming to newcomers. There are online forums, communities, even workshops where you can connect with other people who are interested in quantum computing and learn from the experts.
That's awesome. So it's not just about reading books and articles. It's about being part of the community and getting hands-on experience.
Exactly. And that hands-on experience is so important for really understanding quantum computing. Luckily, there are some great online platforms where you can experiment with quantum algorithms and even run them on real quantum computers.
Wait, really? You're telling me anyone can access a real quantum computer?
Well, not just anyone, but there are platforms like IBM Quantum Experience and Google's Quantum AI platform that let you access their quantum computers through the cloud.
So it's like those cloud gaming services where you
Wow.
don't need a super powerful computer to play the latest games?
Yeah, exactly. You can use a web interface to write your quantum programs and then run them on actual quantum hardware.
That's so cool. It's like making quantum computing accessible to everyone.
Exactly. And it's an amazing way to get a feel for what quantum computing can actually do.
Okay, I'm definitely signing up for a quantum computing course now. We've talked about the potential for quantum computing to change everything from medicine to materials to AI. But what about the less obvious applications? Are there any surprising ways that quantum computing might affect our lives that we haven't thought of yet?
That's a fun question to think about. Quantum computing is such a different way of approaching computing that it's hard to imagine all the possible applications.
Hmm.
But here are a few areas that I find really
Well,
interesting.
they're ready to be surprised.
Okay, so first up, financial modeling. Quantum computers could potentially revolutionize how we analyze, risk manage investments, and predict what's going to happen in the market.
So no more stock market crashes.
I wouldn't say that. But quantum algorithms could help us build more accurate and efficient models for understanding complex financial systems.
Okay, that would definitely interest a lot of people. What else do you have?
Logistics and optimization. Imagine being able to optimize traffic flow in cities, plan delivery routes perfectly, or even design more resilient supply chains.
So no more traffic jams or waiting forever for packages.
Again, it's not about making everything perfect, but quantum algorithms could make these complex systems a lot more efficient.
That would definitely have a huge impact on our daily lives. Any other ideas?
How about weather forecasting? Quantum computers could help us predict weather patterns more accurately, understand climate change better, and even come up with strategies to mitigate the effects.
So better weather forecasts and a better understanding of our planet. That sounds like a win-win.
I think so. And these are just a few examples. The potential applications of quantum computing are huge, and we're still just starting to explore them.
It feels like we've barely scratched the surface of what this technology can do.
Exactly. And that's what makes it so exciting. We're at the beginning of a new era of computing, and the journey is just starting.
This has been amazing. Thank you so much for taking the time to explain all of this to us. It's been a wild ride exploring the world of quantum emulators and the mind-blowing potential of quantum computing.
It's been my pleasure. Remember, the quantum world is full of surprises, so keep exploring, keep asking questions, and never stop learning.
And to all of our listeners, thanks for joining us on this deep dive. We hope you've enjoyed the journey and that you'll keep exploring the fascinating world of quantum computing. Until next time, stay curious and remember, the future is quantum.